If you've never made pancakes from scratch before, it's actually pretty easy. You start with the most important ingredient, the flour, then you add things like baking powder, maybe some salt, maybe some baking soda, some spices like cinnamon. You throw those together, you mix them up, you add in a liquid like water or milk, some people add eggs, and you mix, 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 and you end up with pancake batter. Now, this question may seem a little bit philosophical and odd, but why do we need all these different ingredients? Or why do we need to mix them together? And this really gets at the chemistry that Coach Niobe was talking about. I want you to start off by describing the material properties of these ingredients before you mix versus after you mix. What changes do you notice? Now, were any of the ingredients that we had made out of chemicals? Clearly mixing is important, but are the specific ingredients? Can we just mix together anything? Like if we took, for example, milk and orange juice, would that get us something like a batter? How about milk and dirt? Maybe batter-like, but maybe not the right taste? What about baking soda and flour? Just those two things. Those are some of the ingredients that I talked about. Or how about baking soda and vinegar? Oh, that's an interesting one. I bet you know what happens when those mix together. The point is that you can't just mix together any old stuff and expect pancakes to happen. There are specific ingredients, and we want to figure out a little bit more about why you need the specific ingredients that you do. But before we get to the actual ingredients that we were talking about for pancake batter, we're going to try mixing together some other things. I have for us 6 mystery powders and 6 mystery liquids, and you're going to mix these together. You're going to take a combination of 2 mystery powders and mix them up with 1 mystery liquid. This is kind of fun. You determine your combinations, you get those powders, you put them in a zip bag that you can seal up. You take your liquid, you pour it into a little cup, you drop that cup into the zip bag without spilling it, be very gentle. Then you seal the zip bag up, and then you turn the bag over so that the liquid dumps out, and you shake it all up, and you watch what happens. And then record the results.
Alright, so let's get some powder A. And then we'll get some of the powder E. And here, oh, this is mystery liquid 3. Careful, there. And then we can shake it up a little more.
Now, we don't all have the ingredients to do all of these 6 mystery powders and mystery liquids at home, so what you're going to do is you're going to play with the simulator that I've developed to try and mix these together virtually. When you get to the simulator on the web, you'll see this black box here that represents the zip bag with the 2 powders and the mystery liquid in it. You can select which powders you want to use and which liquid right here at the top. You'll also notice that there's a thermometer here that tells you the initial temperature. Everything here is starting off at room temperature, 23 degrees C. Now the thermometer is not perfectly accurate. It may go up or down a small amount, and there may be slight variations and interesting things that happen, or it might change a lot. What I want you to do before you hit the mix button is to look at the liquid and look at the powders, look at the temperature, look at the texture, and predict what do you think should happen if you just sort of mixed things like this. What do you expect the color to be of the mixture? What do you expect the texture to be? What do you expect the temperature to be? Then click the mix button and watch what happens. Record the results, and when you're ready to try another one, hit the reset button and change your powders and liquids. Let's try one out together. Try powder A, powder B, and liquid 2. Tell me what you think is going to happen. We mixed a dark purple room temperature liquid with 2 whitish grayish room temperature powders. We got something that's a little bit lighter than dark purple, which is what you might expect if you mixed white and purple. And the temperature hasn't gone up or down too much, and the texture is gooey. Nothing too unusual for mixing a powder and a liquid together. Go ahead now and try about 10 different combinations. Look at all the different things that happen. Go ahead and record them and report them here. In a lot of cases, you might have noticed some very unusual things happening, like mixing a white and a pink thing and getting green out. That's an unusual change in the material property. We need to find some way to refer to that. So let's call that for right now a chemical reaction. And this might be our definition of a chemical reaction that we're probably going to return to and add more to as we start understanding more about them. Two students are discussing chemical reactions, and they have these two claims. Which student do you agree with? I think we're ready to enter something into our reasoning library. When you mix two materials together, some combinations of materials have chemical reactions, while other combinations do not. How could you tell that there was a chemical reaction? Well, you already told me most of the things that you observed, but let's go ahead and put them all in one table. There are different examples of unusual changes in material properties. For example, if the temperature changes unusually, it's not surprising that materials get warmer or colder, but when you mix two cold objects together to get something hot, that's unusual. Same thing with color changes. Those are normal, but if you mixed, say, white and red and you got dark purple, that would be unusual. Phase changes are also very normal. That's when you go and get a gas that gets given off, let's say, when you're boiling water. But if you get a gas that's given off without heating things up or cooling things down, that's unusual. We didn't see this in our zip bag simulator, but when something glows spontaneously without any electricity coming in or anything like that, that's an unusual change. Distinct smells are a good sign of an unusual change, probably because there's a new gas that's been released. Where's that smell coming from? And people that have studied chemical reactions in the past might have learned that chemical reactions are not easily reversible. So for example, something that is reversible is a thermometer. It rises and falls, and rises and falls, and it can just go up and down over and over again. But a cake, when that rises when you heat it up, but it doesn't collapse back down when it cools, that makes it unusual, and therefore a sign of a chemical reaction. Here's an example of a chemical reaction at work in everyday life. How many of you have seen these hand warmers? They're not so common in LA, but in colder climates, you might stick them in their mittens or in their boots to keep warm on a very cold day. And the instructions say this: shake them up a little bit, and then locate the inner pouch. There's some material that's in an inner pouch and some that's in an outer pouch, and it says squeeze the inner pouch to break it. Then shake well to mix the contents, a lot like basically mixing the materials together in our own zip bags. Our challenge right now is to design a 2-ingredient hand warmer. Now, all of our simulator results have included 3 materials, but I want you to go ahead and try and see if you can locate patterns in the simulator results so you can pare it down to just 2 of them and tell me what you think is going to be the most efficient hand warmer with just 2 materials. Let's bring this all home. Think about your list of unusual changes that mark chemical reactions, and then go ahead and describe to me what sort of unusual changes happen when you're cooking a pancake.